Hello, welcome to the third lecture for the seventh chapter of Mathematics Class 11, Binomial Theorem. So we were seeing how you can expand, the expressions when you are given, like a plus b the whole power to some index. Okay, so we are dealing with positive indexes. So for smaller power of indices. Okay, so for smaller powers like a plus b the whole cube, we had already we have done these for quite some time. We have seen how they actually expanded. Sorry, if it is there. Yes, b cube. Okay, so this was easy for us to find, but we started facing problems when we had to do like a plus b the whole raised to 5 or a plus b the whole raised to 6. Okay, so we found uh, difficulty in solving for such higher powers. Okay, so when we were expanding, we saw that there were a few rules that were being followed. So the first rule was that the number of terms t, like for a plus b the whole raised to n. So the number of terms t will always be n plus 1. N is your index. And the second rule, or the second kind of pattern that we saw that was being followed, was that the indices of a and b followed a pattern. So what was that pattern that we saw? That if a raised to x and b raised to y, then x starts from n and goes all the way up to 0, and y starts from 0 and go all the way up to your n. So n is your power again. So this was the second rule or second pattern that we saw that is followed by such expansions. And the third one was sum of the indices of the a and b will always be n. Okay, so if you have a raised to x and b raised to y, so for this will be the x plus y. Okay, so sum of the indices of a and b will always be equal to n. Okay, so this is what we had seen. And next, okay, so this is effective. Okay, so this is valid for all such expansions, but how do we get these coefficients? Okay, so this is where we were stuck. So to find the coefficients, what we started with was, or what we last heard was that we use, so we use something called Pascal's triangle. Okay, so as per Pascal's triangle, if you write all the coefficients in the form of a pyramid, okay, so how does that go? So this is your index, and these are all the coefficients. Okay, so we are going to write all the coefficients of the expanded forms, or like the binomial expansions that we say. So we start writing them in the pyramid form. So for index 0, the only coefficient or the only byproduct of anything a plus b raised to 0 would be 1. Okay, so then when your index becomes 1, you will have two terms. Okay, so a plus b, and the coefficient of these are going to be 1 and 1. When it comes to 2, so that actually means a plus b the whole square. So the first and the last term coefficients remain 1, and there will be, since there are, the power is 2, the number of terms is going to be 3. So we have already got the coefficients for the first and the last one. So the middle one, the one that is left, you can find the coefficient of it by adding the two numbers that is there in the previous row. Okay, for when we had index 1. So when you add this would be 2. Okay, so what this means is, like, if you put a triangle, so the numbers on the two upper vertices of the triangle, if you add them, you will get the sum of those two numbers as the value at the lower vertex of this triangle. Okay, and similarly for 3, your first and the last term will have coefficients 1. Okay, so now you are remaining with 2 more terms, because this is 3, so you'll have 4 terms. So for that, what you can do is you add, okay, you add 1 plus 2 over here, this gives you 3, and then you again add 2 plus 1 over here, it gives you 3. Then when you go for 4, similarly the first and the last coefficients will be 1, and the ones in the middle. Okay, so you put the triangle, okay, in between the numbers above the row, or above the row for the index that we are solving, and you add them. So this would be 4, then this would be 6, and this would be 4 again. Okay, so this was what we had derived as or we had seen that this is an example of Pascal's triangle. And using the Pascal's triangle, we had, found the coefficients of higher index also. But what we need for where is the limitation? Okay, so the limitation of Pascal's triangle. Okay, so while it's easy for us to kind of create the triangle all the way up to the index that we want to find the expansion of. Okay, so but the issue comes when in the higher orders, because it's a lengthy process. Okay, so it is a pretty lengthy process, because you have to go all the way up to the the row before the final index that you want to find. Okay, and you have to kind of, it becomes more difficult with very high powers. Okay, so if we want to find, of a plus b, the whole raised to 10 or 12, it will become difficult for us. Okay, so that is why, you have to, kind of go all the way to the row. You have to go all the way to the row right before the desired index. Okay, so these kind of limitations actually makes it difficult for us to always use Pascal's triangle. So the next thing that we use, okay, so which is easier for us to kind of calculate the coefficients for the different terms of the expansion, is if we use, we find the use of the concept of combinations. Okay, so what do you mean by combinations? In the previous chapter, you must have learned that if you have NCR, okay, so this is a combination. Okay, so this N would be the total number of items or that is available to you, and R is something that we take at a certain point of time. So we learn how to do the combination with different values of R. So NCR is actually is equals to n factorial upon the R factorial and n minus R factorial. Okay, so over here your R ranges from 0 to n. Okay, so your R will start from 0, then go up to 1, 2, 3, all the way up to n. Okay, so this is we use the concept of combination to easily derive the coefficients for the expansions. Okay, so this is helpful. The concept of combination is going to be helpful when we want to derive the coefficients for different kind of expansions. Now there are a few rules that we have to remember. So the first value or the rule is that if you have C combination of 0 and 0, okay, that gives you 1. And if your n is equals to R, okay, so you have C and n, so that is also equal to 1. Okay, so this you have to remember. And if you have, say, C of n and 0, so this is also equal to 1. Okay, so these are some that we have to remember when we are trying to do the binomial expansions. Now let's see, in the kind of triangle, okay, so the Pascal's triangle that we were using. So what if we use directly this combinations, okay, in place of, say, doing that addition by putting that triangle, using that triangle relation. Okay, so suppose this is your index, and this is your coefficients. Okay, so when you have 0, your first coefficient would be 0 combination 0, and that is going to be equals to 1. Okay, now the next one, okay, so you have C of 1 raised to 0. Why? Because your R, okay, in this your R will start from 0 and go up to 1. Okay, so 1C0 is going to give you, as we have already seen, if your R is equals to 0, your combination becomes 1. And if you have, the next one is C11. Okay, so if you have N is equals to R, this again becomes 1. Okay, then when you take 2, so your R will go from 0, 1, and 2. Okay, and also we know we'll have 3 terms, so 3 coefficients. So the first coefficient will be 2C0. Okay, so this, if you expand, you will get this again as 1, because if your R is equal to 0, automatically your combination becomes 1. Then the next one is that 2C1, okay, where your R is equals to 1. This will give you 2. Why? Because 2, 1 is 2 factorial upon 1 factorial upon 2 minus 1 factorial. Okay, so that gives you 2 into 1. If you expand, 1 factorial is 1, and 2 minus 1 will also give you 1 factorial. So this is your 2. Okay, so this is how you solve for the factorial. And the last term, okay, will again be 2C2. So your n is equals to R, and that is again is equals to 1. Then the third one that we have, okay, so if your index is 3, your R is going to start from 0, go to 1, 2, and 3. Okay, so the first coefficient will be 3C0. Now this will again be 1. Okay, and the next one will be C1 going C 3C1. Okay, if you quickly see what you will get with this is k factorial upon 1 factorial upon 3 minus 2 factorial. Okay, so you know that if you have n factorial, it will actually start from 1, n minus 1 into n minus 2 all the way up to 1. Okay, so this is how you write a factorial. So this would be 3 into 2 into 1. Okay, and this is again 1 factorial. And this will be 3 minus 1. So 3 minus 1 is 2 factorial. Now 2 factorial is also 2 into 1. So you can cancel out 2 into 1 would be 2. So 2 and 2 cancels out and you get 3. So your 3C1 is equals to 3. So similarly, you can write that 3 over here. And the next one is C3, 3C2. So this, if you actually, write it in the factorial form, you will get 3 factorial. Okay, R factorial is 2 factorial. And n minus r is again 1 factorial. Now this is in the same form as your previous coefficient. Okay, so you can immediately think that this would be 3 again. So this is equals to 3. And the last, this would be shifted a little. So this you have 3, 2, this is also 3. And then you have the last one. So that is your 3, 2. Okay, and this will be 1. So you see that it is easier now for us to, kind of calculate the coefficients for, different kind of powers. So if you have, suppose your index, now we are not going to write it in the triangle form, as you can see that it takes up a lot of space and also it is lengthier and you cannot see the steps very easily. So I will just write it in the normal linear fashion. So index, suppose we have is 4 for say a plus b the whole raised to 4. Okay, so the coefficients, what would be your coefficients? You can directly write them first. So first you will have n is equals to 4 and r will start ranging from 0, 1, 2, 3, 4. Okay, because r, the number of values that r can take is 5 and we will also have that terms would be 5. So the final terms of the expansion will also be 5 in number. So the first terms coefficient would be, okay, so 4C0, then we have 4C1, 4C2, 4C3, 4C4. Okay, so you have got your 5 coefficients for the 5 terms. So the first one, okay, 4C0 is going to be 1 itself. Okay, when we go for 4C1, you can write this as 4 factorial upon 1 factorial because r is 1 over here and the other one is 4 minus 1 factorial. Okay, we will write. So we will directly write it as 3 factorial. Now, as we had seen, suppose, you have C4 or, just the factorial form. Okay, so 4 factorial can be written as 4 into 3 into 2 into 1. And we know that 3 factorial is equals to 3 into 2 into 1. So this part, okay, so the this part of the 4 factorial, okay, so this part of the 4 factorial can be written as 4 into 3 factorial. So what it does is that if you write it in this reduced form or simplified form, you can just cancel out if the same factorial value is appearing in the denominator. So when you write this, you can write this when you get 4 factorial upon 1 factorial into 3 factorial, you can just write this as 4 into 3 factorial. 1 factorial is 1 into 3 factorial. So 3 factorial and 3 factorial gets cancelled. You are left with 4. Okay. So 4C1 is equals to 4. Now let's see for 4C2. So 4C2 would be is equals to 4 factorial upon your r factorial is 2 factorial, and 4 minus 2 is also 2. So 2 factorial. Now again, if you write 4 into 3 into 2 factorial, okay, so one of the 2 factorials can get cancelled, and 2 factorial is what? Is 2 into 1, so that is 2. So 2 and keep 1 2 factorial, so factorial is cancelled. 2 1 2, so this is 6. Okay, and then the fourth term would be 4 factorial upon your r factorial, so that is 3 factorial, and 4 minus 3 factorial is 1 factorial. Now you see this is similar to the form of 4C1. So this for 4C1 we had got 4, so the similar ways 4C3 can be written as 4. Okay, now the last one you have is 4C4. Okay, so because your n is equals to r, this will become 1. So therefore, the coefficients are 1, 4, 6, 4, 1. So therefore, now if you expand a plus b the whole raised to 4, okay, so the first term, okay, since we will now follow all the 3 previous rules also that we have seen. So it will start with a raised to 4. And since the first coefficient is 1, you don't write anything. So it's 1. So the next term's coefficient is 4. And you will have A4 was the first term. So the next term would be A3. And you will get B plus 6. Now A squared, B squared plus 4 again. Okay. So because the fourth term has the coefficient 4 again. We have A, B, Q plus, now the last one is 1, and so we have B raised to 4. Okay, so this is how it's easier for us to use the concept of coefficients for getting this. So now let's see a higher kind of binomial expansion. So you have A plus B the whole raised to 6. Okay, suppose this is what we want to know. So the coefficients, okay, so first let's write the coefficient would be what? They will be starting from 6C0, 6C1, 6C2, 6C3, 6C4, and you have 6C5, 6C6. Okay, so you will see you will have 7 coefficients because we have 7 terms. Now let's find the values of all the coefficients first. So this will be 1. And then you have 6C1. So 6 factorial upon your r factorial is 1. And you have 6 minus 1 factorial, so that is 5 factorial. Now we can easily write this as 6 multiplied by 5 factorial upon 1 into 5 factorial, and we will get 6. Okay, now the next one is 6C2, so that is 6 factorial upon 2 factorial, and this would be 6 minus 2, 4 factorial. Again, simplify so that you can take out the higher factorial in the denominator. So 2 factorial is 2 multiplied by 4 factorial. So 4 goes away, 2 ones are 3. So this is your 15. Okay, so your third term's coefficient would be 15. Then you have C6, C3. So your R factorial is 3 factorial, and when you have 6 minus 3 factorial, so that is 3 factorial again. So 6 into 5 into 4 into, say, 3 factorial. Okay. Expand one of the factorial, so 3 into 2 into 1. So let's keep the 1 out, and then you will have 3 factorial again. So 3 factorial goes away. So 3 into 2 is 6. 6 also goes away. So what you're left with is 20. Okay. Now the next one would be 6. Sorry. Right. Yeah. So the next one is 6C4. Okay. So now you have 6 factorial. Your R is 4. So 4 factorial. 6 minus 4 is again 2 factorial. Okay, so this is the simplified term is equal to what we had for 6C2. Okay, so 6C2 is similar, so you can just write that as 15. Now you will have 6. Yeah, so you have 6C5 now. So that would be 6 factorial upon 5 factorial here, and 6 minus 5 is 1 factorial. This is again same or similar to the coefficient, it will be the value would be same as when you have 6C1. So this was 6. Okay. And the last one, your 6C6 is going to be 1. So therefore, when you write A plus B the whole raised to 6. Okay. So combining all the previous rules that we know about the variables, okay. So the first term and the second term. So what we get is, so the first coefficient is 1, so let it be. So the first one will be A raised to 6 and B raised to 0. So that is also not written. Then the next coefficient, okay, is 6. And now your A or the index of A will decrease by 1. So this will be 5. And for B, it will increase by 1. Then the next one, the coefficient is 15. And A becomes A raised to 4 and B raised to 2. Plus the next one is 20. So you have A raised to 3 and B raised to 3. Then the next one you have, 15 again. And this time you have A raised to 4. A raised to 2 and B raised to 4. Okay. And then plus you have the next one is again 6. And that is A, B raised to 5. And the last one is B raised to 6. And there is only 1 as your coefficient. So this is your expansion. Okay, and we can very quickly get the coefficient for all the terms of the expansion when we are using the combination concept. Okay, now let's see a higher one. So you have A plus B the whole raised to 8. Excuse me a minute. Okay, so the coefficients for this would be 8C0, 8C1, 8C2, 8C3, 8C4, 8C5, 8C6, 8C7, 8C8. Okay, so you'll have 9 coefficients because we have 9 terms. So let's see, the first one will be 1. Okay, then the next one is 8C1. So that will be 8 factorial upon 1 factorial. R is 1. And then you have 8 minus 1 factorial. So that is 7 factorial. You can again write it as 8 into 7 factorial upon 7 factorial is equals to 8. Okay, now the next one is 8C2. So you have 8 factorial upon your 2 factorial, and 8 minus 2 factorial is 6 factorial. So you can, in the numerator, okay, so you can expand the factorial up to your largest factorial in the denominator. So 8 into 7 into 6 factorial. 2 factorial is 2 and 6 factorial. So this get cancelled to 1 and this is 4. So 4 into 7, you have 28. Okay. Now the next one, you have 8C3. So this would be 8 factorial upon 3 factorial multiplied by 8 minus 3 factorial is 5 factorial. So let's expand. So 8 into 7 into 6 into, keep the 5 factorial as it is. Then 3 factorial is 3 into 2 and 5 factorial here. So this gets cancelled. 3 into 2 is 6. 6 gets cancelled. So you have 56. Okay. Then the next one you have 8C4. So this is 8 factorial upon 4 factorial. Okay. And 8 minus 4, 4 factorial. So that will be 8 into 7 into 6 into 5 into 4 factorial. Okay. You can expand one of the 4 factorial. Okay, 4 into 3 into 2 into 1, let it be. You won't write that. So you have 4 factorial. So 3 into 2 is 6 gets cancelled. Okay, and 4 and this becomes 2. So you have 7 into 5 is 35. 35 into 2 is 70. Okay, now the next one is C 8C5. Okay, so that would be 8 factorial upon you have 5 factorial and 8 minus 5 is 3 factorial. You can see that the form, okay, the form or the value that we would get would be equal to what you get as 8C3. Okay, so that is 56. And the next one is 8C6. Okay, you write it in the factorial form. 8 factorial, you have R factorial as 6 factorial. 8 minus 6, okay, 8 minus 6 would be 2 factorial. This again becomes similar to the value that we had already got for 8C2. Okay, you can see this is the same, and then this would become 28. And the next one would be 8C7. Okay, 8C7, and what you get is, so 8 factorial upon, you have R factorial, 7 factorial, 8 minus 7 is 1 factorial. This is similar to your 8C1, and then again that becomes 8. And the last one, that is 8C8, is equals to 1. So therefore, your A plus B raised to 8 can be written as, your first coefficient is 1. So, and you start with A raised to 8. Then you have the second coefficient is 8, and you have A raised to 7B, plus you have 28, the next one. So 28, A raised to 6, B raised to 2, plus you have the fourth coefficient as 56. So that is A raised to 5, B cubed, plus the next one is 70. So you have A raised to 4, B raised to 4, and then you have 56 again as a coefficient, and that is your A cube, B raised to 5. Okay, then you have plus the next one is 28, and you have A squared, B raised to 6, and then you have 8, A, B raised to 7, and the last coefficient is 1, so you have B raised to 8. Okay, so again, easier for us to simplify and write the expanded form when we are using the concept of coefficient. Now let's take an example and solve. Okay, so suppose you have, okay, so suppose we take the question as x plus 5 raised to 7. Okay, so this is what we want to find. So we can first, start off by first finding all the coefficients. Okay, so we have not done the calculation of, the index 7. So the coefficients that we will have are is 7C0, 7C1, 7C2, 7C3, 7C4, 7C5, 7C6, and 7C7. Okay, so this is what we have, and we want to find. We want to find the coefficients, and then we want to expand the x plus 5 the whole raised to 7. So let's start with finding the coefficients. So you have 7C0, so that is 1. Then you have 7C1, so that is 7 factorial upon your r is 1. So 1 factorial, and 7 minus 1 factorial is 6 factorial. So you get this as, you can expand 6 factorial, cancel it, you will get 7. Okay, so this is your second term's coefficient. Then you have 7C2. So this becomes 7 factorial upon 2 factorial, and 7 minus 2 factorial is 5 factorial. So you can again expand your top, your numerator part to, you leave the remaining factorial. Then 2 factorial is 2, and then 5 factorial you write as it is. Cancel out 5 factorial, and 2, 3. So you have 21. Okay. Then the next one is 7C3. Okay. So this you can write as 7 factorial upon, you have r factorial is 3 factorial. You have 7 minus 3 is as 4 factorial. So expand 7 factorial up to you reach your 4 factorial, product. So 7 into 4, 6. So 7 into 6 into 5 into 4 factorial. 3 factorial you can expand. So 3 into 2. And you write 4 factorial. 4 gets cancelled. 3 into 2 is 6. So you get this as 35. Okay, so you get 35 as your 7C3 term coefficient. Then you have 7C4. Okay, so this is again 7 factorial, and then you have 4 factorial, and 7 minus 4 is 3 factorial. You can see this is equal to the previous, previous coefficient that we had. The form is the same. So you can just write the value as it is. So this is 35. Then the next one that we have is 7C5. 7, 3, 5. Okay, so you have 7 factorial upon 5 factorial, and 7 minus 5 is 2 factorial. This is again similar to your 7, 3, 2 coefficient, and that would be 21. Then the next one you have is 7c6. So you have 7 factorial upon r is 6, so uh, r factorial becomes 6 factorial, and then 7 minus 6 is 1 factorial. You can see that this is again similar to your 7c1, and then you get that as 7. And the last one you have 7c7. Okay, and that becomes 1. So the coefficients that we get are, okay, so the coefficients we get are 1, 7, 21, 35, 35, 21, 7, 1. Okay, so when you have x plus 5, the whole raised to 7. Okay, so you have x plus 5, the whole raised to 7. You can write this as, you write your first variable for first term as x raised to 7, okay, and 5 raised to 0, so you leave that out. The first coefficient was 7, okay, so with 7 you write, now you have x raised to 6, okay, and multiplied by your b is 5. The next one, the coefficient was 21, okay, so I'll just write out the coefficient for 21. 55, 55, 21, 7, 1. Okay, so the next coefficient is 21 into now x raised to 5 multiplied by your b squared. Okay, it becomes b squared, so 5 squared. 5 squared is 25. Now you can first write all in terms of their indices, so it's easy for us to understand. Then the next one is 35 into your a raised to 4 becomes x raised to 4, and b raised to 3 will become 5 cube. Then you have plus the next term's coefficient is also 35. Now this becomes x cubed multiplied by now your 5 raised to 4, plus you have 21. Okay, so 21 into x squared multiplied by 5 raised to 5, plus the next one is 7. So 7 into x into 5 raised to 6. Okay, and then you have the next one. You have only 1 as your coefficient and there is no x. So the last one is 5 raised to 7. Okay, so now let's expand. So you have 7 into 5, so that is 35 x raised to 6. Now this is 21 into x, 5 into 25 plus 35 into x raised to 4. 5 cube is 125. Okay, then you have again 35 into x cube. 5 raised to 4 is 625. Then you have 21 into x squared into 625 into 5, which is 3125. Okay. Then the next one is 7 into x into 5 raised to 6. So 3125 multiplied by 5. So you get that as 5, 2, yeah, 1, 5, 6, 2, 5. Okay. And the last one you have as 5 raised to 7. So that is multiplied by 5. Okay, so this is what you get in the expanded form. Okay, so where you have got you have written it in the general form of a plus b, the whole raised to 7. Okay, so this is what we get. So now you multiply all the coefficients, and our second term is a number itself. So we have the values for that. So the final result that you get is 21 into 25 is 25x raised to 5. Then the next one is 35 into 125. So that is 4375x raised to 4. And then you have 35 into 625. So that is 21875x cubed. Then you have 21 into 3125. So that is 5625x squared. Okay, and then you have 7 into 15625. We have 5, 3, 7, 1, 2, 3, 8, 5, 9, 9, 10. Okay, so this is 1,09,375x plus 78125. Okay, so this is your expanded form. Still a bit tedious when you have some numbers in the expression that you are being asked to solve. Okay, but it is easy for us to now get all the coefficients. Okay, so you can just use your combination. Okay, so NCR, and from whatever your n is, your r starts from 0 and goes all the way up to n. It is easy for us to calculate the coefficients for each of the term, and then you can simply put your coefficients for the different terms, as well as the respective powered indices or terms. Okay, because we already know the rules that we have followed with respect to your the way the indices will change for your two of your terms. Okay, so it is easy now. We have seen that we quickly went into understanding how combinations along with the Pascal's triangle, okay, can be useful for us to solve the binomial expansion sum. So we will end today over here. And in the next class, we will have a few more examples that we can solve using the combination concept. And we will also move further in the chapter where we will be, we have a proof that we will be seeing how, what is the proof and why is it, useful for us after that. So thank you.